Tonight and tomorrow at the workshop session, I hope to share some data with you and show you where it leads. And the result is that this data ends up giving us a very young universe, a very young creation. I've been involved in this research for about 26 years now, and I've learned that God doesn't lie in his creation, and so the data that we get from the created order around us can be trusted. So what I want to do tonight is to start with some basic physics. Now, don't let that scare you. My wife has been training me to talk in simple English, and she's still succeeding, and I have still a long way to go, but we'll just do the best that we can. And tomorrow, in the 3-hour session, there'll be other fields that I'll be talking about in astronomy and geology and so on with the young universe and the young Earth. So in this first session, I hope to be putting together some pieces of a puzzle, rather like a detective looking for clues. The clues indicate that there are at least 5 anomalies that can't be readily explained by current theories as they stand. Now, what do I mean by anomaly? Let's think that we've got some sort of theory to work, and then some data comes in which disagrees with it. This is totally discordant. What are you going to do? Throw out the data or throw out the theory? This is an anomaly. You've got theory and data not in agreement with each other. Well, for example, if you had a theory that all dogs were white and a black dog came along, what are you going to do? You're going to either accept the data that black dogs do exist, or are you going to change the theory? Or are you going to throw the data away and say, no, whatever happens, my theory is correct, and all dogs are white? Well, that's the sort of option that science has today. God didn't lie with his creation. And so as a consequence, we can face the data that we get from the created order with some sort of courage, knowing that God can be trusted. So, okay. The clues that we're talking about indicate there are at least 5 anomalies which can't be readily explained by current theories as they stand. We'll discover that these 5 anomalies that currently accepted theories can't explain, currently accepted ideas can't explain, lead in fact to a new cosmology. What do I mean by cosmology? Well, it's a study of the universe and what has happened and when and how and why. So as we have a look at these 5 anomalies, it turns out that we can develop a new cosmology, a new way of looking at the universe, a new way of looking at astronomy and geology and physics and so on. And we find that this inevitably leads to a young creation. In this session, we want to examine some of these anomalies and some of the controversy, as you like to say it over here. I come from a different country, as you've probably gathered by my speech. I feel a bit like Peter there at the fire warming himself just before the crucifixion, and the maid says to him, "Your speech betrayeth thee." So, okay. So, as we have a look at all of these 5 anomalies, it turns out that there is one basic cause. Any one in itself would indicate that our theory is faulty, but we actually have 5, or at least 5, to deal with. The 5 anomalies together give us prima facie evidence that science has missed some key item in their understanding of the cosmos. And when this item is factored into their thinking, a new cosmology develops, which gives us a young universe. This cosmology is a reassessment of astronomical and geological evidence and the timescales used, and it's going to be discussed in the workshop sessions tomorrow. So for this first session, we need to familiarise ourselves with the 5 areas of current theory which are inadequate. We note to begin that the Hubble Space Telescope supplied a lot of new data and has overturned many ideas. As a consequence, Big Bang math have had to add parameters which they never expected to have to add in order to get agreement between data and theory. In addition, some observations have shown that the further out we go, the more problems we have with the math, with the Big Bang data. Now, because the math, as they have it standing at the moment, fails to explain what we're actually seeing out there. So there's actually a different formula which agrees with the data out there, and this is a warning sign that there is a theory in trouble here. So we need to reassess Big Bang modelling. Now, scientists are not liars. They try to look for the best fit for the evidence, and the evidence does seem to indicate an expanding universe. But the Bible was way, way, way ahead of them, because at least 12 times in the Bible we're told that God created the heavens and then stretched them out. Well, let's look at the evidence that they found which led them to their theory of the universe. And we call it the Big Bang today, a Big Bang or a big expansion. And as it turns out, this evidence, or a lot of it, has been misinterpreted. And they've got themselves into a lot of bother as a result. The whole idea of the Big Bang started in the late 1920s with the discovery of the red shift of light from distant galaxies. Now, some of you may not be familiar with the red shift. Let me take a moment to explain. As you take light from the sun and put it through a prism, it breaks up into the 7 rainbow colours that you're all familiar with. The rainbow does this automatically for us. The Lord has worked that in a very beautiful way. Now, as you have a look at this colour spectrum, as we call it, you have a look at these colours in detail, you find that there are sets of dark lines on them. And these dark lines come from various elements that we have in the sun. Each element has its own characteristic set of dark lines, rather like a barcode. Each element has its own barcode, or spectral lines, if you like. So that when we look at a star, a distant star, and we pass its light through a prism and we get this barcode, these spectral lines, we know exactly what elements are there in that star. So when we look at distant galaxies, we get spectral lines from all of the stars. And the important point is that the further out we look in space, the further down towards the red end of the spectrum, all these dark lines are shifted. And we call this the red shift. And here we have an illustration of what is happening. I think they've taken the line of calcium here. Here's the double line there. Here's our laboratory standard up here on Earth for these dark lines. Notice on this galaxy, the lines are shifted down this way a little more. It's further away. On this one, it's shifted a little bit more because the galaxy is further away again. And on this one, look how far it's shifted from the laboratory standard, which is way back here. This is a very distant galaxy, and those spectral lines, those dark lines, are shifted down towards the red end of the spectrum, the lower energy end, very significantly. Now, the graph of redshift against distance is standard. It shows that the redshift increases with distance in a very precise way. Thanks, sweetheart. Here's the redshift distance graph. What we have here is the redshift coming up along here compared to distance along here. 1 indicates the origin of the cosmos. So see how the redshift is getting progressively greater and greater and greater, very significantly so, the closer that we get to the origin of the cosmos. Now, recent observations by the Hubble Space Telescope show that the graph was actually steeper than expected early on. It was coming up like this. What does the graph mean? Well, it means the further away a galaxy was, the greater is the red shift. Now, they needed to explain why the red shift was in existence. And what they did was to talk about the stretching of the universe. Astronomers thought initially that it was something like a Doppler effect. You're familiar with this. As you are on the highway there and a police car comes screaming up behind you with its siren going, the pitch drops as it passes you and you sort of heave a sigh of relief. And the pitch drops, and so you've got a longer wavelength coming to you as the police car is racing away. And astronomers thought, okay, the same thing is happening with light. These galaxies are actually racing away from us, and the light waves are therefore stretched in the same way as the pitch of the siren drops. And so the redshift values increased with distance. And so if the Doppler approach was followed, it implied that the cosmos was expanding faster at greater distances along here. Therefore, the cosmos expanded faster in the past and got slowed down by gravitational forces. You can understand that if the galaxies were initially racing away, and then you have gravity tending to slow this process happening. Well, Edwin Hubble of the Hubble Space Telescope fame questioned this explanation of the redshift in 1929. He suggested it initially, but he also questioned it. You see, the problem was that the redshift are simply numbers, like 1, 3, or 2.547, something like that. They are simply numbers. But the redshift that you find over here, these are the numbers. These are the numbers. But what you found on that other diagram that we had with the spectral lines being shifted, you actually had a velocity there, talking about the rate at which these galaxies are moving away. And velocity is measured in kilometres per second or miles per hour or something like that. But the redshift is simply a number. 1, 2, 3.54, whatever. So there was a problem. Hubble was not necessarily sure that it was valid to put velocity values against such numbers, but many others accepted the explanation. But there have always been some astronomers who have questioned the explanation, but the majority accepted it. Now, while most agreed that this was the interpretation of the redshift, that is, that the galaxies were racing away, another approach to the data was achieved with the same result. A new mathematical basis for the expanding universe was formulated by a gentleman called Lemaitre in 1931. It was an extension of Einstein's relativity. Einstein's approach was that you had a static cosmos in which the galaxies were racing away from each other, in which the galaxies were moving through it. The universe itself was not expanding, but the galaxies were moving. The problem was that some of these galaxies at the frontiers of the cosmos must have been moving pretty close to the speed of light. This meant that there'd be such forces operating on them that they'd disrupt. And the Lemaitre approach was different. He said that the fabric of space-time itself was actually expanding. And as a consequence, the redshift would follow, because what would happen is that a light wave in transit through space, as space expanded, the light wave would get stretched and become longer and longer the longer it was actually travelling through space. And so this proposed that the light waves were stretched in transit as the fabric of space expanded. Therefore, you can get a redshift this way. Now, this approach is generally accepted by many scientists, but not all. The Doppler expansion explanation has been promoted by the popular press, and some astronomers still hold to it. But the interesting thing is that the math and the equations are still basically the same, no matter which approach you have. So the problem has arisen with the new Hubble Space Telescope results, because they only work if the expansion rate has actually increased with time, not decreased. This took them by surprise. Neither approach predicted this result initially. This was an entirely new development which had to be factored into their equations. But either way, the redshift was the foundation on which the Big Bang was built. And the redshift equations, as I said, were the same in both cases. But a problem surfaced to both approaches in 1976, and it's been with us ever since. This problem threw an entire monkey wrench into the whole idea of this Big Bang. Both approaches predict that there would be a smooth change in redshift with distance. Something like a car with if you have your foot down on the accelerator at a steady level, the car smoothly accelerates with its speed increasing steadily until you reach a stable speed. Well, another idea is that if you have an apple falling from a tall tree, the speed gradually builds up until the apple hits the ground. Well, as it turns out, the redshift doesn't do that. Instead, it appears to go in a series of jumps. It's quantized. You have quantities, which are there in clumps. So what happens is something like, if we go back to our car, the car, if you have your foot on the accelerator, would travel at 5 miles an hour, 5 miles an hour. Suddenly it would jump to 10 miles an hour, 10 miles an hour, another jump 15 miles an hour, 15 miles, another jump 20. It doesn't happen like that out there with our car. It would be the same with the apple. If that fell from the tree, 3 miles an hour, 7 miles an hour, 10 miles an hour, and it doesn't work like that. You can see the sort of problem that astronomers are getting themselves into. So this jump is what these groups of measurements is called a quantization. Well, naturally the finding was highly disputed. The more measurements that occurred, the trouble was the more it appeared. It all started with William Tift, a professional astronomer over in Arizona, back in 1976. And astronomers were aghast at this development because it threatened the whole base on which the Big Bang was resting. They expected it would be easy enough to disprove the redshift quantizations simply by getting more measurements. Here they were saying, okay, we're not going to throw out our theory, we're going to question the data to start with. In 1981, an extensive redshift survey was published by Fisher and Tully, and the redshifts did not appear to be clumped, as Tift had suggested they were. And astronomers breathed a sigh of relief and said, see, there we are, our problem is not really there, we just needed more data. And then it was discovered in 1984 that if you subtracted from that data the actual motion of the solar system through space, it turned out that all redshifts right across the whole sky were going in jumps. They were quantized. In 1985, well, of course, this was unacceptable. In 1985, two astronomers, Salentic and Arp, were not expecting to find any redshift quantization in their measurements. Instead, it turned up in their study of 260 galaxies. They were looking for something entirely different, and the redshift quantization turned out. In the mid-1990s, Guthrie and Napier set out to disprove it, and ended supporting it with 399 galaxies. They had difficulty in getting some of their work published as a result of this. Now, here is Guthrie and Napier's graph. You have distances out here, and along here you actually have, these are measured in velocities, kilometres per second. And notice here you have systematic peaks where you have the red shift is at a stable level. Then there's this trough here where there's no change in the redshift, then another change there, another change there, and so on. And one astronomer pointed out rather boldly and said, rather courageously, one can see at a glance how accurately the troughs and peaks of redshift march metronomically outwards from 0 to over 2,000 kilometres per second. On the 5th and 7th of May in 2003, there were two abstracts in Astrophysical Journal by Morley Bell, who announced further evidence. The second abstract read in part, evidence was presented recently suggesting that galaxy clusters studied by the Hubble Key Project may contain quantized intrinsic redshift components that are related to those reported by Tift. In other words, he's seeing the same thing as Tift saw. Here we report the results of a similar analysis using 55 spiral and 36 type 1a supernova galaxies. We find that even when more objects are included in the sample, there is still clear evidence that the same quantized intrinsic redshifts are present. Wow. The issue of the redshift quantization refuses to go away, even though astronomers are still arguing. In fact, it's given astronomers a bad name. They throw out the data and they want to maintain their theories. There's a story which goes something like this. The head astronomer came in from a university to the head mathematician in the university. And he said, I've just made a marvellous mathematical discovery. Oh, said the mathematician sceptically, what is it? Oh, said the astronomer, it turns out that all odd numbers are prime. Oh, said the mathematician. Yes, said the astronomer. 1's an odd number and it's prime. 3's an odd number, it's prime. 5's an odd number, it's prime. 7's an odd number and it's prime. 11's an odd number and it's prime. 13's an odd number and it's prime. Just a minute, said the mathematician. What about 9? You can divide that by 3. Oh, said the astronomer, that is just observational error. Okay. Well, this whole idea of the quantized redshift is fatal to both current versions of universal expansion because it requires that expansion to go in jumps. There's other evidence that the redshift quantization is not a speed or a velocity. As you have a look at the Virgo cluster of galaxies, for example, you find a redshift quantization right throughout the Virgo cluster except in the very centre. And there in the centre, the motions of galaxies are so high that it starts to wash out the quantization. So, okay, this means that motion is not giving you the red shift. It is rather washing out what you've already got. Even worse, they found that some redshift quantum changes cut right through the middle of some galaxies. What does this mean? Well, it means that if the redshift is a motion or is a velocity, it means that your galaxies are going to be split in two and they should be disrupting. This isn't happening. Okay, well, if the redshift is not due to space expansion and it's not a velocity, the whole basis for the Big Bang is called into question. And all this places astronomers in a dilemma. Do you want to uphold a model, a theory, or really find out what's going on? This anomaly and the failure of the math at high redshifts is a sign of a theory in trouble. Is there an alternative? Well, yes, there is. There's actually a very viable alternative, and we'll be discussing this in the workshop sessions tomorrow. As it turns out, light emitted from atoms in galaxies will actually give you the same formula, and the problem that you have with the mathematical variation at high redshift can be overcome rather readily. What it means is that atomic orbit energies gave rise to redder light back in the early days of our cosmos. In other words, the orbit energies were a little bit lower than what we have today. And there's a reason for that. And this reason comes down to the basic reason why we have these anomalies. So this approach directly relates to the explanation for the other 4 anomalies in a young universe. So the problem with the redshift is one of the 5 anomalies that present theories can't account for, but they're all easily explained if one additional piece is added to the puzzle. Well, let's list off the 5 anomalies. 5 anomalies with one cause. We've already mentioned the quantization of the redshift. That's this one down the bottom here. We've already discussed, and I'll explain some of the others in detail. Scientists have been examining the sizes and behaviour of atoms and atomic particles, and they've assumed that they've always behaved in the same way that they're doing today. And these behaviour patterns have been formulated in terms of constants, atomic constants, because they're describing or meant to describe atomic behaviour. As it turns out, some of these atomic constants aren't constant at all. We have decreasing values of the speed of light. We have increasing values of Planck's constant, and we'll talk about this in a minute. There's increasing values of atomic masses and slowing atomic clock rates. These 5 anomalies are all children of the same parent. They all have one thing in common. The key is biblical. It gives a new cosmology, a young universe, a young earth, and it will be explained in the workshop. But for now, let's refocus our minds on these other 4 anomalies that present problems that theories can't account for. And we start with the speed of light. The speed of light we have here as the shorthand, mathematical shorthand, is the letter C. So if I lapse into mathematical shorthand and say that C has changed, you know that it's actually the speed of light that's changed. Okay. The declining speed of light was a major topic of discussion in the scientific journals from the mid-1800s until 1941. As an example, The astronomer M.E.J. Guri de Bray was quoted in the journal Nature on the 4th of April 1931 as saying, and I quote, "If the velocity of light is constant, how is it that invariably new determinations give values which are lower than the last one obtained? There are 22 coincidences in favour of a decrease of the velocity of light, while there is not a single one against it." In the 350 years of the measured values of the speed of light, 16 different methods have been used, and there have been 164 different determinations of its value. It is generally true, with some exceptions, that the measured speed kept decreasing, and this was the cause of the scientific comment. And it was true even when the same method were used, or the same equipment was used by the same person many years later. In fact, we've got 17 examples of this. The later the measurement by the same equipment, the lower was the value of the speed of light. In 1886, Simon Newcomb, in the journal Nature, published on May the 13th, commented that the values of the speed of light obtained by the methods used around 1740 were consistent among themselves, but placed the value of the speed of light around 1% greater than what they were in the 1880s. In 1941, the physicist R.T. Burge, who kept track of all the values of these atomic constants, spoke of the speed of light values obtained by a variety of methods in the mid-1800s. Ironically, some of these methods were used by Newcomb. And Burge acknowledged in the journal Reports on Progress in Physics that, quote, "These older results," including the ones that Newcomb got, "these older results are entirely consistent among themselves, but their average is nearly 100 kilometres per second greater than that given by the 8 more recent results." Here are astronomers and physicists who do not believe in a change in the speed of light, saying, well, the measured values, in fact, have dropped with time. About that time, the physicist N.E. Dorsey stated, "As is well known to those who are acquainted with the several determinations of the velocity of light, the definitive values successively reported have, in general, decreased monotonously." So there was a systematic trend downwards in the measured values of the speed of light that couldn't be denied. And there's a great deal of discussion about it in the scientific journals back in those days, and over 50 articles in one top journal alone. The discussion was all the more impressive because the speed of light was generally held to be a constant. The problem was that if the speed of light was changing, it was going to be potentially disruptive to the new physics that was developing. And it was more particularly the case in some atomic constants were also changing, whereas others were constant. The reasons why were unclear. Burge, who was the keeper of the constants, as I mentioned him earlier, he kept track of these variations right up until 1941, August of 1941. Then something strange happened. He wrote an article in Reports on Progress in Physics on the general physical constants, quote, "with special reference to the speed of light." The introductory paragraph read in part, listen to this: "This article is being written upon request and at this time," his emphasis, upon request. "A belief in any significant variability of the constants of nature is fatal to the spirit of science as science is now understood." This closed the whole discussion. All the changing values of the atomic constants and the speed of light, okay, they're not changing at all. Ignore the data, we'll run with the theory. All the constants were declared constant and physics was not going to be sidetracked. Their theory was going to be intact. So the issue was now buried, but it was not dead. The trend in the atomic data continued. This way of doing things is not science. It's not, at least it's not good science. Science should look at the data. Why was Burge so upset back in 1941? Well, if c was high, if the speed of light was higher, it inevitably led to a chain of reasoning which showed that there was not enough time for evolution. And tomorrow we'll show you how this all works. But for now, they knew that evolution had to happen, and so the speed of light had to be constant. I started investigating the changing atomic constants and especially the speed of light back in 1980. In early 1987, we had an invitation to write a major white paper on the atomic constants for internal review at Stanford Research Institute International, SRI International. It resulted in a 90-page report, The Atomic Constants, Light and Time, co-authored with Trevor Norman and myself. All told, there were 638 measurements of 12 atomic quantities by 41 different methods, published jointly by SRI International and Flinders University in August of 1987. The data trend was compelling. The Professor of Statistics at Flinders University gave us 100% support and asked us to prepare a seminar on it because the whole math department was very, very excited with what we were doing. And around about December of that year, in December 87, V.S. Troitsky from Russia published in Astrophysics and Space Science the evidence that there was a decline in the speed of light over the lifetime of the cosmos, and associated atomic constants were also varying. Pardon me. This was similar to what we had reported. And then someone contacted SRI International and Flinders University and said, "Are you aware of the fact that this research leads to a young universe and is against the theory of evolution?" I was banned from the math department at Flinders University. My co-worker, Trevor Norman, eventually lost his job at Flinders University because of this. In 1993, a Canadian statistician, Alan Montgomery, and a US physicist, Lambert Dolphin, examined all the statistical criticisms which were coming in since 1987 and re-examined the data trends in the 87 report. They published a statistical analysis in a peer-reviewed journal which has never been refuted. What was the conclusion? The conclusion was that the analysis gave full support to the data trends that we had outlined in our 87 report. Since then, a variation in the speed of light has almost become a respectable idea among some astronomers and cosmologists. For example, Moffat in the 1990s, and Albrecht and Meguijo in 1999, John Barrow in 1999, and many other astronomers stated that many astronomical problems would be resolved if you had a very high value for the speed of light at the inception of the cosmos. Paul Davies followed this up in 2002, and there's been over 50 articles about this ever since. One problem: they have adopted what they call a minimalist approach. This means that they're varying the speed of light and only other things that are absolutely necessary. They are not conserving energy in the process. And here's where the problem comes in. If you're not conserving energy, in the equation E equals mc squared, m is constant, c is going sky high, so the energy from any given reaction must also be going sky high. The work that we had done in the report in 87, and I spent months on this trying to find out what was happening, as some quantities were going up, others were going down, some went part way. I juggled my equations around. It turned out that this whole thing only worked if energy was being conserved in the process, so that as the speed of light went higher, atomic masses were lower. And so you actually had a position in which it wasn't a minimalist position, but it was a position in which energy was conserved, and you find that all of your physical and chemical processes remain in balance. These guys are not doing that. And I had a chance to talk with Professor Albrecht at Davis a few years ago, just after his report came out. And I said to him, "Why are you dropping the speed of light dramatically shortly after the beginning of the cosmos?" He said, "Well, we couldn't get the data to agree with other constants if we didn't do that." I said, "It will work if you conserve energy in the process instead of adopting this minimalist position." He said, "Yes," he said, "we looked at that, but he said, if we conserved energy, we could not achieve all we wanted to do with our theory." Okay, they're not running with the data, they're running with the theory. So, okay. So, with this work which we did in 1987, we'd not isolated the basic cause. What we had was a reason why things were behaving the way that they had, but we'd only have one part of the puzzle. And it turns out that when the basic cause is in place, all 5 anomalies are explained, and the speed of light is only just one effect, although a very important one, but it was not the primary cause of the 5 anomalies. So we come back to the actual fact that the speed of light has been measured as slowing. And in summary, we have this graph of the speed of light behaviour from Burge. Yes, Burge, this is Burge's graph. This is how the speed of light behaved according to Burge, his best possible values. So, okay. So all the data is in the report, and that's available on our website. And the Montgomery Dolphin articles on statistics also demonstrate the reality of this drop by the various methods. Okay, can we have the next slide, sweetheart? What we have here on this slide is another physical quantity called the Rydberg constant, in which all 5 or all 4 of these 5 quantities are actually varying in such a way that their variations cancel out. Look what happens to the result. Here you have effectively a straight line, a constant value. You've got a couple of outliers here. You have a scatter around the average position. This is the sort of thing you should be expecting with the speed of light and all the other data that we've been questioning. It should be looking like this. But it doesn't. In fact, it comes down or it goes up or whatever. So the third anomaly is Planck's constant, H. Now, Planck's constant measures a special kind of radiation in the universe, and we'll talk more about that later, but it's been defined as a constant. But nevertheless, as you have a look at these values, they've been increasing with time. These are the officially recommended values for Planck's constant H. H is the mathematical shorthand. See how the recommended values have varied over time. These values were determined by a scientific committee which had examined all the measurements, and these are the best possible statistical value. The recommended value carries the weight of scientific authority. So the graph shows how this value has changed. Notice something here, because we'll pick this up a bit later. It seems to peak around about 1970 and then perhaps a change in direction. Keep that in mind. Okay. Now, let's have the next graph, sweetheart. The officially recommended values of Planck's constant over the electronic charge is this one. Again, we've got Planck's constant. Look at the similarity of this graph to the one that we had for Planck's constant, although H over E, Planck's constant over the electronic charge, is measured by an entirely different way of doing things. But nevertheless, you still have this increase which peaked around about 1970 and seems to be tapering off. Okay. The experimental values show that Planck's constant has been steadily increasing. One reviewer of the report that we issued back in 1987 had this to say. He said that the instrumental resolution may in part explain trends in the figures, but I admit that such an explanation does not appear to be quantitatively adequate. And in 1965, J.H. Sanders in the Fundamental Atomic Constants on page 13 pointed out, quote, that the increasing values of Planck's constant can only partly be accounted for by improvements in instrumental resolution and changes in accepted values of other constants. In other words, this increase in H in Planck's constant is anomalous. Current theory cannot account for this. The point is that Planck's constant has been measured as increasing with time. But as it turns out, Planck's constant times the speed of light is an absolute constant, even astronomically. It means that the speed of light and Planck's constant are inversely related via this common cause, When one goes up, the other goes down. And it turns out there's an extremely good reason why. It turns out also that Planck's constant is a direct measure of this basic cause. The fourth anomaly is atomic rest masses and the behaviour of atomic particles. Some atomic processes have been measured as changing, not just Planck's constant and the speed of light. An important example is also directly related to the basic cause, and that's atomic masses, atomic rest masses or electron rest masses. We've got electron rest masses measured here, but it also applies to all other atomic particles. Again, the graph shows atomic masses rising to 1970 and then flattening out just like Planck's constant did. And we need to know why they're doing this. And we'll discover there's a very viable reason why these quantities are varying in the way that they do. The fifth and final effect of the one basic cause is the rate of ticking of the atomic clock. Now, the atomic clock is based on the rate of movement of particles within the atom. Remember, God said in Genesis 1:14 that the sun, moon and stars were given to us to be for signs, for seasons, for days and for years. In other words, the sun, moon and stars were to be our time measure. We had an orbital clock. The time it takes the Earth to go around the sun once. This is God's time measure. As it turns out, with the math and everything which has been done with this work, this clock is ticking at a constant rate. It does not change with all the other changes that we've been talking about, even given the basic reason for these changes. Science, however, in the last part of the 20th century, took the atomic clock as its measure of time because they could get very, very small divisions of time. You get electrons whirring around atoms very, very fast. So you get small divisions of time. You can chop this thing up. And it has been assumed that radioactive dates from the atomic clock are the same as orbital dates. They are assuming that the atomic clock is ticking at a constant rate. Well, a comparison between orbital time and atomic time was done from 1955 to 1981 and published by Dr. Thomas Van Flandern, who was at the US Naval Observatory in Washington. He said, as the conclusion to his study, the number of atomic seconds in an orbital interval is becoming fewer. Presumably, if the result has any generality to it, this means that atomic phenomena are slowing down with respect to orbital phenomena. You getting the drift of this? The atomic clock is slowing with time. It means it was ticking faster in the past, so it means that your radioactive dates are systematically too old. Since then, many astronomical observatories around the world have noticed this discrepancy, and the slowdown up to 1970 again was picked up, and atomic clocks started to run faster than that. Now, thanks, sweetie. This is the graph of the rate of ticking of the atomic clock compared to our orbital dates. Look at this. The atomic clock is slowing, again down to about 1970, and then it is starting to go up again. Something strange is happening here. This atomic clock rate follows the same pattern as the light speed curve. It bottomed out around 1970. The slowdown to 1970 increased after that, and radioactive clocks are similar, and the decay rates, because decay rates are governed by the same factors. We're getting close to the end here, so hang in just a bit longer. The C measurements now can be used, the way that C is measured now, the speed of light is measured now, is by using atomic clocks. But wait a minute, that atomic clock was slowing, and the speed of light was slowing. If you're measuring a slowing speed of light with a slowing atomic clock, you're not going to notice any difference. Okay. It's like having defined your second as somewhat longer And so your minute is going to be inevitably longer as well. So here's where we have a problem. One is moving lockstep with the other. So the C measurements that we obtain now can't detect changes in the speed of light because the atomic clocks are moving lockstep with them. Now, even Burge noticed this back in 1934. He was a very canny individual. He found that wavelengths of light didn't change when the speed of light did. And he concluded, if the value of the speed of light is actually changing with time, but the value of wavelength in terms of the standard meter shows no corresponding change, then it necessarily follows that the value of every atomic frequency must be changing. Atomic frequencies are the rate at which the atomic clock is moving, or how fast atomic particles are moving within the atom. So all atomic clocks tick at a rate proportional to the speed of light. And the graph of the speed of light behaviour is basically the same as the rate of ticking of the atomic clock. And since atomic clocks, including radioactive clocks, ran faster in the past, radiometric ages are not orbital ages. The number of times the Earth has gone around the Sun is not the same as the number of ticks on the atomic clock. The two things are measuring time in a different way. Their years are not the same. The atomic clock, the radiometric clock, give ages which are systematically too old. And in the workshop tomorrow, we'll be talking about the mathematical correction that we can apply to the atomic clock. And when we do that, it turns out that all of your radiometric ages, all of the immense astronomical and geological ages can be fitted into a framework in which we have in the scriptures. And the time problem is resolved. So in summary, 5 separate anomalies are involved, all behaving synchronously. They all have one basic cause. Well, what is the common factor in all of these anomalies? Let's go back to the Bible. Remember how we said initially that God created the heavens and stretched them out. One statement in the Bible occurs 12 times. It's important enough if we take the Bible as saying something even once. The fact, we have a number of examples here. We're told in Isaiah 42:5, "Thus saith the Lord God, who created the heavens and stretched them out." Or Jeremiah 10:12, "God has made the earth by his power, established the world by his wisdom, stretched out the heavens at his discretion." Or Zechariah 12:1, "Thus saith the Lord, who stretched out the heavens, laid the foundation of the earth, and formed the spirit of man within him." It's always in the context of creation week, and usually in the past tense. And the Hebrew action implied in all of that is that it's completed an action. So the first point to note from this is the expansion of the universe is already completed. In other words, the universe is not expanding now. It was completed at the end of creation week. In other words, we have a static cosmos. Now, this disagrees with majority astronomical opinion. But there is a number of minority astronomers who hold that we do have a static cosmos, such as Nalika and Arp. In 1993, they pointed out that a static cosmos will be stable and will not collapse, but there will be slight oscillations of the cosmos. And we'll talk about this in detail tomorrow, but that is why we have this change in direction for the atomic constants in 1970. And this is in full agreement with the Bible, full agreement with the quantized redshift and other observational evidence that will be mentioned later. But let's return to the scriptural statement that God expanded the heavens. How does this cause the 5 anomalies that we've mentioned? To understand, we need to dig just a bit deeper. And let's see what's happening as the vacuum of space was stretched out. If I take a rubber band and stretch it so I can hit the person in the back seat there, I've actually added energy to the fabric of the rubber band. If I blow up a balloon and let it go, you know what happens. I put energy into the fabric of the balloon. When God expanded the heavens, he put energy into the fabric of space, the vacuum of space, in the same way that energy has gone into the fabric of the balloon or the rubber band. But isn't space empty? Next one, love. Isn't space empty? Not really. If you take a sealable container, the 18th century view was that if you pump out all solids, liquids and gases, here's your vacuum pump, you pump out all solids, liquids and gases out of your chamber, you should have a perfect vacuum. Well, in the 19th century it was realised that there's going to be some temperature radiation in here. So if you have a refrigerator unit there put in and cool the container down to absolute zero, that is 0 degrees Kelvin, about minus 273 degrees Celsius, or about minus 460 degrees Fahrenheit, you would then expect that you would have a perfect vacuum. But instead, can we go up just a bit further, love? Thanks. Instead, it finds that there's an intrinsic energy in the fabric of space. It's called the 0 point energy because it was there even at absolute zero of temperature, 0 Kelvin. Robert Matthews in New Scientist for 1995 described it as follows. The 0 point energy, the ZPE, is a turbulent sea of randomly fluctuating electromagnetic fields or waves. At the macroscopic level, the level that you and I are used to, space is smooth or even featureless. But at the level of atoms, it's like a seething vacuum, like the spray around the bottom of a waterfall. Many physicists have calculated the energy in 1 cubic centimetre of the vacuum. And to coin a word, it's absolutely ginormous. Let me give you a feel for this. Here's 1 cubic centimetre. At home I have lights which run from electricity rated about 150 watts. The sun radiates at 2 million times greater than that. In our galaxy, there are something like 150 billion stars, all radiating at approximately that rate. If you had all of our galaxy of stars radiating at that rate for 1 million years, that is the energy in 1 cubic centimetre of free space. And that is maintained for 20 billion light years in every direction. This is the energy that God has put into the fabric of space as a result of his stretching. The 0 point energy. It's absolutely ginormous. It's incredible. And back in 1911, Max Planck demonstrated that Planck's constant, H, is a measure of the strength of the 0 point energy. And that energy has been proven to exist experimentally. It's called the Casimir effect. As you bring two metal plates close together in a vacuum, you find that there is a force tending to collapse the plates together. What is happening is that as you bring those plates together in a vacuum, you are effectively excluding those wavelengths of the 0 point energy which will not fit exactly between those plates. And that excluded radiation, those excluded wavelengths, are exerting a pressure on those plates which is collapsing them. So the closer the plates get together, the stronger the force. And it's been measured to within 1% accuracy in 1997 and 1998 by Lamoureux in some very beautiful experiments that were done. Incidentally, sailors notice the same effect when they're on the ocean. If they bring two boats closer together than one ocean wavelength apart, boats tend to collide. So the Casimir force is very strong at molecular distances and attracts and gives an attractive force between molecules. The 0 point energy manifests as noise in electronic circuits, which limits amplification of signals. It also is the reason why you need pressure to solidify liquid helium. Well, if the ZPE is there, why don't we notice this all-pervasive bath of electromagnetic radiation? For the same reason that we don't notice the 15 pounds per square inch pressure on every part of our body due to the atmosphere. That pressure is balanced inside and out. And I can touch Penny with a lightest touch of the hand. It's nowhere near 15 pounds per square inch, but she notices that difference in pressure. And so it's only a difference that we get between this background 0-point energy. Anything over and above that is noticeable. But there's another important puzzle to solve. If God said he stretched out the heavens and gave rise to the ZPE, as we had with the balloon and the rubber band, we've already noticed that Planck's constant H is measured as increasing with time. This means, if we take the values of H at face value, that the ZPE strength must have increased with time. One might ask why. Well, there's a very good reason why, and we'll return to this aspect of the topic in the workshop session. But for now, let me give you a rough analogy. If you put a cold plate of food into a hot oven, it takes a while for the food to build up to the temperature of the oven. As the ZPE builds up with time, for the same reason, the energy that was put into the fabric of space takes a while to manifest as the 0-point energy. So the ZPE builds up with time, and as it does so, the properties of the vacuum alter. Light speed slows down for reasons we'll give you tomorrow. Atomic clocks slow down for reasons we'll give you tomorrow. Planck's constants and atomic masses increase for reasons we'll give you tomorrow. And the red shift, remember where we started, the red shift actually decreases with time. It works with simple math, it works intuitively, it works biblically, it accounts for all the data, nothing has to be thrown out. We don't need to invent dark matter, dark energy, missing mass, or anything like that to support an invented failing theory. So tomorrow, we'll put it all together in the workshop session. And the time scales involved compared to the orbital period of time that we're used to measuring, the atomic times, we can actually supply a correction to these atomic dates. And when you do, a new cosmology emerges which allows us to harmonise astronomy and geology with the Bible. Thank you very much.